The stage at which we typically have the most control is choosing the sample from the sample population, because the target population is defined by your research question. The sample population is often restricted by practical constraints, right? I literally don't know how to find people in the US other than by this list of phone numbers. The respondents from the sample, I don't get to force anybody to participate in my study, or right, I can't do that. I don't know how to force them. But sample from the sample population, if you give me a list of phone numbers, I have total control over how I choose from those phone numbers. If you have people walking by me in front of the Science Center, I have total control over which ones I decide to approach. So typically, we as study designers have the most control over choosing a sample from the sample population. And for this reason, there are the most statistical methods, the most math theorems, the most research about how to choose a sample from a sample population. But I want to make sure we're putting this in context. Choosing the sample from the sample population is important. It's no more important than figuring out how the sample population relates to the target population. And it's no more important than figuring out how the respondents relate to the sample. The only reason that there's so much more to say about how we choose a sample from the sample population is that we have the most control over that, and so people have thought a lot about how to do it. So just to draw a little mini version of this picture so we can see where we'll be focusing as we go on. Let's see, I drew blue and then green, so I can go to the next slide and remember that. Here's my sample, right? Actually, wait, yeah, so that's my sample population and the green is the sample. Okay, that's my sample population, and then I drew a green triangle and that's my sample, right? Okay, so that's what we're going to focus. We're next going to describe some sampling methods to give you a sense of some different ways for choosing a sample from the sample population. Not all of these ways are created equal. So one way I might do this is haphazardly, right? I might stand in front of the Science Center and like reach out to whoever is kind of closest to my elbow, or I might reach out to people who look most friendly. To give total honesty on this, I once did a survey like this when I was with a haphazard sampling process. The summer before I was a senior in high school, I was doing a survey at a particular place, and my job was to approach people in a waiting room to ask them about the service that they were about to receive. And honestly, what I did is I was 16 years old, and I went up to the people who looked most friendly. Was that a good idea? Well, no, that's a terrible idea for getting a representative sample, right? But it is what I did. I did, make a little visualization at the end of that project. And it's not that uncommon, actually. So there could be a haphazard sampling method, right? Haphazard, or you could also call it a convenience sample. This is kind of like putting a link on Facebook and seeing who responds, right? That's a haphazard or convenience sample, right? That is likely not going to work very well. Why? Because the units who end up in your sample are not going to be representative of the sample population. So likely not representative. Okay, what would be better? I'm not going to stop and answer your question about this, but I think a lot of you probably have a word in your mind. What is the best strategy to use for choosing a sample from a population? How should it be? Should it be arbitrary and for convenience, or should it be random, right? That's the word, hopefully that's in your head. It should be random. So there's lots of different ways to choose a sample randomly. It would not be enough to say, we're going to select a sample randomly from the sample population. So let me list a few of the ways that we might do that. The most famous way, actually not the most common, although it's the most commonly discussed way to choose a sample from a sample population, is a simple random sample. And that is usually abbreviated SRS. I'm going to give you the kind of practical definition, and I'll give you in words the mathematical definition. So the simple random sample is where all the units in the sample population are put in a hat and a predetermined number, of units is selected. Okay, take all those phone numbers on that list, right? Maybe I cut them up. So there's one phone number on each piece of paper. I put them all in a big hat and I draw 100, right? That is a simple random sample. If I'm trying to take a simple random sample of Wellesley students, take every Wellesley student's name, put them in a hat, mix them all up, pull out whatever number, 50 of them, right? That is a simple random sample. Mathematically, what that means is that all subsets of size, whatever you chose, say size n, have the same probability of being the sample. Okay, so suppose I'm going to draw 50 Wellesley students. Every subset of Wellesley students of size 50, every set of 50 Wellesley students that I could think of has the same probability of being my sample. Okay, so what kinds of things does that mean? That means that the fact that you're in the sample does not make it more likely that your roommate's in the sample, right? It means that just because I included a few people from one dorm doesn't tell me anything about whether certain other dorms are going to pop up. Every subset of size n has exactly the same probability of being the sample in a simple random sample. So simple random samples are attractive because we all understand this idea of putting names in a hat, and also because it's mathematically simpler to deal with. All the possible subsets of the same size have the same probability. For this reason, the simple random sampling technique is the default assumption for most common statistical inference methods. Let me say common statistical methods. For example, if you have seen a t-test before, which I think you have, a t-test assumes simple random sampling. Now, is that true in most cases where you might have run a t-test? Nope, right? It's usually not true. But if you run a t-test, you're assuming you have simple random sampling. So in that extends to lots of other methods. Simple random sampling is the most understandable. It is mathematically attractive. It's the one we assume when nobody tells us otherwise. Is it actually how we collected our data? Probably not. So I'm going to list a couple more. We won't spend a lot of time in this class trying to use data that explicitly we know was collected by other methods. But I do want to just mention what some of these other sampling techniques are, because I think you should have a list of those so that you realize that saying random sampling is not specific enough. There are other random techniques other than simple random sampling. So other techniques include stratified sampling. So that involves grouping the units based on some characteristics, such as dorms, and then you take a simple random sample from each group. Based on some characteristics, has to be something that you observed ahead of time, and then take a simple random sample from each group. So again, with Wellesley students, it might be that I make a list of dorms, and then within each dorm, I put a bunch of names in a hat and draw a sum, right? Or I could do it by major. Maybe I want to make sure that I don't accidentally end up with a simple random sample that is mostly STEM majors, right? That would not be representative, especially if I'm interested in something that is academically based, like how students like remote learning. So I could take each major, for each Wellesley major, put all the names of students in that major in a hat and draw a few of them by simple random sampling. And that would ensure that my final sample included people from every major, and that's called a stratified sampling method. Note that this method does not meet the mathematical definition for a simple random sample. It's no longer true that every set of 50 Wellesley students has the same probability of being my sample, right? Because it's now not possible that all the math majors end up in my sample. With simple random sampling, it is possible. There is some chance that I'll get all the math majors. But with stratified sampling, I'm very specifically taking a subset of each major or a subset of each dorm. And so there's no chance that, say, all the math majors will end up in my sample. Other methods include cluster sampling. This one is more for convenience or practical constraints. You don't want to do cluster sampling unless you have to. The idea here is you divide the units into clusters like majors or dorms, and then take a simple random sample of the clusters. So instead of putting names of students in a hat, I put names of dorms in a hat. and I choose 2 dorms, and then I go talk to every student in each of those dorms. Or I put names of majors in a hat. I choose 10 majors, and I go speak to every student who's in one of those 10 majors. So now I know for sure that I'm not going to get a sample that includes people from every major, right? So this is still not a simple random sample. There's 0 probability I'm going to get a sample that includes every single major, but this is really convenient because I might only have to walk over to a couple dorms. So again, divide units into clusters, do a simple random sample on the clusters. Okay. There are others that I'll just list here quickly. One is systematic sampling. That's the one that is most commonly used for the scenario I gave you with people walking by me and the table in front of the Science Center. Here you include every kth unit. So I might stand in front of the Science Center, and every 7th person who walks by, I'm going to try to include in my survey, right? That's systematic sampling, and it's random because I start at a random point, right? So I might say, okay, here's the first 7 people. I'm going to do simple random sampling from those 7 to decide which one of the first 7 people to ask, and from then on, I'll do every 7th person. So therefore, that's a random sample because there's randomness in it. I could have started in any of the first 7 places, and I'm going to take every 7th unit. But this is not a simple random sample because there's 0 probability that people who come in consecutively are going to be included in my sample. This one, so notes here, this one is helpful for convenience. That's usually when we end up doing this clustering sampling. Systematic sampling is useful because it's sequential. So anytime when you don't start out with a list of everybody in your sample population, but rather they're approaching you one by one, systematic sampling can be helpful. So again, for this idea where I'm standing in front of the Science Center, this can be helpful. I have personally used this for exit polls, right? You stand in front of a polling place and people walk out and you might approach every 7th person. Or this is used by doctors who are doing medical studies of rare diseases. People keep on showing up with rare diseases, but you don't start out with a list of all the people who are going to get some rare disease in the next year, right? Rather, every time one shows up, you could either take them or not, and you might take every 3rd person who arrives with this rare disease in order to include them in your study. The last one I'll mention here is Bernoulli sampling. For Bernoulli sampling, it's also sequential. You flip a coin, which might not be a fair coin, for each unit to decide whether or not they'll be in your sample. Flip a coin for each unit to decide whether they are in your sample. This one is also sequential. So I have done studies like this too, right? So maybe what I'm going to do is as people approach me when I'm standing in front of the Science Center, I'll flip a coin, and if it's heads, I'll try to include them in my survey, and if it's tails, I won't. Again, that's helpful if you don't start out with a list at the beginning of who's going to be in your study. For this method, Bernoulli sampling, this is not simple random sampling because you don't even know how many people are going to be in your sample when you start, right? I don't know how many heads I'm going to end up with total as people walk by me in front of the Science Center. So I haven't even predetermined my sample size. So the point here, right, the point is that random sampling is not the same thing as simple random sampling. Rather, simple random sampling is an example of random sampling. And it's simple random sampling that is our default assumption when we are using most of the common statistical methods.